Okay, terrific.
Yep, good, thank
Okay,
you.
so this integration defines what the delta function is. And if you look at a pictorial representation of what the delta function is, it looks something like this. It's just a spike, right, at a specific point in 2D at a point in the plane. And you can move that spike around in the plane. It doesn't have to happen at 0, 0. You can move it off to some point in the plane. Let's say that point is eta psi. And so when x is equal to psi, then the spike will occur in the x direction. When y is equal to eta, it occurs in the eta direction. So you've moved that thing off to some other point than 0, 0. You can also create a two-dimensional or a line delta function that is, connected delta functions all down a plane like this. You define that as a function of L, where that's defined as a line in the plane parameterized by L and theta. So this actually should be delta L comma theta. And that will give you something that would sift out a line of values through a function when you integrate it across. And then this is a very classic function in linear systems and all of imaging. It's called the sampling function. And remember, when we make a medical image, it's a finite set of values. For example, an MR image could be 256 by 256 or 512 by 512. At each one of those pixels, you have a value. And so it's a discrete image. So it's points, and then you display those points on the screen. Those points are approximating a continuous function that you assume is the truth underneath. And this is the way this function is used mathematically when we need to sift out those discrete points, right, from the object. So if we want to sample a function at specific locations, we use a delta function that has deltas separated by some kind of sampling rate, right? And this is what's done in all digital imaging and what's done in all digital music, for that matter, right? Is that you have a sound wave and you collect data at a specific rate and you represent that continuous sound wave with finite numbers separated by a very short space in time, right? And you encode each one of those amplitudes of the numbers and you stick that in a file, an MP3 file, and that's the music, right? So we're going to learn a number of classic functions that are used in linear systems and that are used in imaging all the time, both CT and MR. And this is one of the first. This is called the rect function for rectangle. And the way it's defined in the book and the way we'll always use it, it's 0 as it approaches the origin, and then at -0.5, it goes up to 1 to unity. Then at 1 unit long, then it goes back down to 0. Okay, so it's 1 unit wide, that's 1 unit high. And that's used often to describe a window. So if you have a function and you just want to sample it in a window, you would multiply it by a rect function that is situated at some point that is your window. Right? So you can imagine we have some continuous function like so, and then we multiply it by this rectangle. It just chops off all the rest of the function. We'll say we don't care about that stuff out there. And what's very interesting to note is what does that do to the frequency spectrum, in the Fourier space of that function? Obviously, it changes it because you've added this sort of discrete cutoff, right? So it's good to know the Fourier transform of this thing. You should have it in your head, right? And the Fourier transform of a rectangle function, when you take its Fourier transform over to Fourier space, it's called a sinc function. It's a beautiful looking sombrero type function where it has a central peak and then it oscillates, and it rings down. The amplitudes of those oscillations decrease, and they decrease as 1 over x, where this is x, where this could be frequency if this was time. And it has this classic ring down appearance. Okay, so we'll see how this happens, why they're This is the Fourier transform of a rectangle function once we look at the Fourier transform. But just looking ahead, this Fourier pair is something that you need to carry around with you all the time. And after this course is done, you will have this for the rest of your life. You will know that, oh, if I truncate data here, then in Fourier space, I have this ringing thing that I have to multiply by. In 2 dimensions, you can make a rectangle function exactly the same way, basically, that we just did. You just multiply an x rectangle function with a y rectangle function. This means this function is actually separable. It's a multiplication of a function that is only a function of x times a function that is only a function of y. And so we'll see that this has certain properties because it's separable. And now we have basically a square in the plane. And inside that square, it's 1. So that's our field of view where we're interested in things. Outside, it's multiplied everything to 0. And the Fourier transform of this square looks like this in 2-dimensional Fourier space. You can imagine if I go along the frequency axis in the y direction, I get a sink, and I get a sink this way. And then this is what the off diagonals look like. So it too is a bulge around the origin in Fourier space, and it rings down. And we'll look at that in more detail. You need, as we move along, for those of you, I mean, you're all in master's program, right? Everybody's a master's student, so we all know about complex numbers. But just as a review, complex numbers are a great way to do certain types of math because you can have amplitude and phase. It's a very efficient, compact notation. With 2 numbers, you can also, quantify it as an amplitude of a vector and a phase of a vector. And so the magnitude of the vector in the plane is just as you would compute it just in Euclidean geometry, right? The component squared, square rooted, that's the length of the vector. And then the angle of the vector in the plane is just how you compute it from grade 10 math, which is the arctan of the ratio of y over x. J has interesting properties, right? J squared is -1. When you have 2 complex numbers, 3 plus 2j and 3 minus 2j, and you multiply them together, you just multiply them out the way you would, by expanding things in parentheses. And you can see from in this case, the product of those 2 complex numbers is a real number, right? Because the j squared appears here and the other j terms cancel out. And so that means the 3 plus 2j is sticking up in one direction, the 3 minus 2j is down the other direction in the plane. And when you look at the amplitude of the multiplication of those 2 vectors, you get a real number and no base term. So we're going to use the complex notation because it is such an efficient way of dealing with functions in which we look at sines and cosines. Right? When we're looking at spatial frequencies or oscillations, looking at complex numbers is a great way to do that. And the reason it's a great way to do that is this miraculous formula here. This is called Euler's equation, and it's generally regarded by many of the world's greatest physicists and mathematicians to be the most beautiful equation in the world. It just, when you first look at it and you get it, like you understand what this is actually saying, it's not obvious that it's true at all, right? It's like, why on earth would this be true? In the sense that E is like the banker's number, right? It's the number that when you compound interest at shorter and shorter intervals such that you're compounding interest every microsecond, you ask, how much do I earn in a year? You get this number. It's like 2.718, whatever. And it's a transcendental number. It's a fantastic number and everything. So that's how that number is derived. What the heck does it have to do with sine and cosine, right? Is the first mystery, like when you're in first year or whatever, you're looking at this guy, why is this true, right? And did you have a question?
Yeah, it's a so there's a j, so
Yeah. I would use J. I mean, in electrical engineering, it's pretty universally used J. If I comes out because you did an undergrad in physics or something like that, that's fine. We'll understand like what's going on. But it normally in linear systems and double E, J is used. I don't know why. I don't know the history of that, but in physics, I mean, I did an undergrad in physics, and we used I all the time. So that's, but anyway. So anyway, one way of figuring this out and coming to terms with this equation, saying, oh yeah, this is true, is write out the Taylor series, right? Write out the Taylor series of this. Just use the formula for the Taylor series and write it out for this, write it out for this, and write it out for this. And lo and behold, those two Taylor series are the same darn thing, right? And so then it starts to make a little more sense. Okay, well, at least using the, sort of these differential things. The other thing is that E, like when you take its derivative, it's itself, right? So the derivative of e to the x is e to the x. And what does that sound like? Well, the derivative of cos is sine, and the derivative of sine is negative cos. So you get that cyclical infinite derivative, right? So it doesn't matter how many derivatives you take, you still have a value, and they're cyclical, right? And so you can see then kind of why this works out. It's absolutely beautiful. So if you want to work with sines and cosines and things that oscillate, it's a compact, beautiful notation to use this thing, e to the ij, or e to the j theta. Okay, and we'll put a magnitude in front of it as well. Okay. Okay. So cosine itself is the real part of, and this is obviously from physics book, real part of e to the ix. It looks like this equation, and sine is the imaginary part of e to the ix. It looks like this. And we'll see when we're looking at Fourier transforms of things like e to the ij or e to the j theta that these terms will come up. 3D complex function phasor. Oh, okay. What did I want to say about this? Well, in 2 dimensions, we have e to the j, and this whole thing here now is theta. And in the plane, you can derive a theta value just by plugging in an x and y, and then these 2 constants here. And the reason we're looking at this is because in magnetic resonance imaging, when you collect the image and you set certain things on the scanner and the level of the gradients and things, you are essentially adjusting these constants, right? That's what you're doing. And so understanding that this e to the j theta, all of this is just a phasor. It's a unit length vector that's rotating around in the plane. And this is the theta value in the plane. And we're going to set these constants with our imaging coordinates. And so you can break it up into its real and imaginary parts. So let's take a look at some of these functions in the plane, where we have, in this case, u sub 0, from the equation, oops, here, u sub 0 is equal to 1, and mu sub 0 is equal to 0. And so, oh shoot, keep going the wrong way. So this is equal to 1, this is equal to 0. This goes away, then we have this left, right? So that means as we run along in the x values, right, we have mu sub 0 equals 1, and we're going to go through the cosine function, right? So we have here, we're going to go through this function. And it creates a plane wave such that I have oscillations in the X direction. I do not have oscillations in the Y direction. When I switch that constant to 2, I get twice as many oscillations as a function of linear dimension. 4, get twice as many more. Now it gets interesting when I click a value in for mu naught. So now I have a value for Y as well, such that if I move in the Y direction, I get a sinusoidal oscillation in the Y direction at this frequency. But when you look at it, it looks like a plane wave that's traveling in a specific direction, right? And it turns out when we create an MR image, we adjust these two values to create different plane waves in the signal from the patient. And it's plane waves in the starting phase of the radio frequency energy that's going to come out. And so understanding when I have this equation, right, and I'm changing mu naught and nu naught, I'm essentially changing a plane wave in different orientations such that when they're equal, I move away on a 45-degree angle and I'm looking at the direction of that plane wave. This was a typo in the electronic book. It should be this script S. So it should read like this, where you have, we're going to do an input-output equation for a continuous system. So if I have an object, which is a two-dimensional function in the plane, fxy, and we put it through this system, and it comes out as gxy. Our system, can be whatever our imaging system. If I have a continuous real object that's the God-given thing, and it's a set of brightnesses, and then I sample it with my system and I make a picture, right? That is all bound up in this thing here, this S, and it will create my image GXY. And usually what happens is that thing is blurred in some way compared to the truth. And sometimes it can be geometrically distorted. If it's optics, you can distort it. Turns out in magnetic resonance, it can be geometrically distorted as well. If for instance, the magnetic field is not uniform or the gradients aren't uniform. So all of that is wrapped up in this system. Now, this is the definition of what a linear system is. And most of the time when we're looking at the analysis of how you take pictures and how you analyze what's in the picture, we assume that the system that made the picture is linear because it makes a lot of things easier. And so there's one fundamental principle of a linear system is encaptured in this equation. All of these equations are just taken straight out of the textbook. So all of this is in the textbook. When you read through chapter 2, you get another explanation of this. So what linear means is if I have a sum of, say, capital K different pictures or objects, right? So I have capital K different objects, and I add up those objects into a new object with different weights. And then I send that into my linear system and I get a GXY. Okay? I'll get exactly the same answer if I take each one of those individual objects, send it through my system. Now they're over here and I've got a set of GXYs and I add those up with the same coefficients, right? So it doesn't matter what I do first. If I add up the objects and then send them through the system, or send each object individually through the system and then add up the outputs, I get exactly the same answer. Very powerful concept, right? And it comes up in practical work all the time. When you're looking at something and saying, does it matter if we do all these first and then add them up, or should we add them all up first and then send them through this system, right? So this is the definition of linear system. And it leads to a lot of very simple truths when you know your system is linear. For the most part, imaging with MR, for example, is quite linear, right? So, and for that matter, for CT in most situations. Now, this is what's called the impulse response of the system. And it's also called the point spread function system. So we've already seen this. We have an input, which looks like a ellipse here or a disk, but in fact, we're modeling it mathematically as a delta function at some place. It's at psi eta, right? And that's the input to the system. And then I get an output, right? Which is some blurred image, but it can also have ringing and some other effects like that. Okay, and that's the point spread function of the system, right? And ideally, the system is shift invariant, and that means that if I have this delta function here at the center when eta and psi are 0, or I move the delta function off to the edge of my field of view of what I'm taking, when that goes through, I get the same point spread function. That means it's shift invariant. And what are we doing here? Oh, okay, we're developing shift invariance here. Thanks. So if I have some input, again, you can go back to the textbook. These equations are straight out of the book in this section. And I, have my object input as such. I convolve it with my point spread function of the imaging system. And if we can assume that that point spread function basically just doesn't change with eta and psi, okay, we make that assumption, we can then replace that point spread function with a shift invariant version of the point spread function. So it's the same regardless of zeta and phi. When that is true, it means that the image that you get from your system is the underlying object itself convolved with the two-dimensional point spread function. Okay, so I take, my perfect object. All I have to do to understand what GXI is do the convolution of the point spread function with the object, and that's the image I'm going to obtain if it's shift invariant. Okay, and so the equations, when you go back in the book and look at this derivation, this is basically showing you why that is true if it's shift invariant, right? And if it's not shift invariant, you can't make this claim, and it makes things harder, right? So if I have a central field of view in which, I have a certain sharpness and a certain point spread function, and then off to the edges, it blurs more, it's not shift invariant, right? And then we can't just say that our image is convolved with one specific point spread function. So convolution, just to remind you what convolution is, graphically, if I have a function f and a function g in one dimension, right, what I define as the convolution of f with g is the following. You flip g around with respect to its, if this is the x-axis, we flip it around the x-axis such that it is reversed, and then you pass that reversed version of g across f, and at each click that you pass across f, you calculate the product of the two of those functions, and you plot that as the value, okay? And so you get, in this case, something that looks like this. As g overlaps with f, you start getting positive values as you get some overlap with that integral. You reach a peak when g is maximally, overlapping with f in this case, and then as g moves on, here we get a decay. So it's important to remember that the convolution involves this initial flip of the g function, and the x-axis before you do the moving it across and taking this integral. The cross correlation of f and g is when you do not flip g, you just cross correlate the two by putting g over here and then moving it across f and calculating these overlap intervals like so. Right? And then autocorrelation doesn't involve g at all. It just involves f convolved with itself. Is autocorrelation, or g convolved with itself. Right. Yeah.
So for convolution, it's the multiplication of f and g, but for the second one, the cross correlation, it's the integral.
It actually, the convolution has an integral. So they're identical, except for the fact that in the convolution, you flip g first in the x direction, and you reflect it in the x direction, and then you do the integral. But you're still doing integral, and we'll come to the formulas for all these. Okay, so I don't know why there's no formula. Do I not have a formula here? I don't. Okay. But pictorially, this is what convolution is. And it turns out that the reason convolution is defined with this flip will also become apparent later. I mean, it's not obvious, like why, when you first look at this, you say, well, why don't you just call the cross correlation the convolution? Like, you know, what's special about flipping G? And we'll see when you define it like this, there's a theorem that's involved with taking the Fourier transform that works out really nicely. And that's why it's defined like this. When we have these linear shift invariant systems, and you can just classify your system with one point spread function like this, then it becomes really easy to cascade these functions. So if you have a two-stage process in your image, and the first stage has the point spread function h1, the second stage has the point spread function h2, right? Then it makes it quite simple to combine these things. In that, all you have to do is convolve this with this, and that gives you the output of the system. Okay, you don't have to pass f through h1 and then pass f through h2. Right? You can just convolve h1 and h2, and that gives you the output of the system. Okay? Here, this one's more obvious, that if you pass f1 through h1 and your image through h2, you get these two copies of the difference, and you add them to get g, that you can just add these two together to achieve the same thing. And again, separable systems, we won't dwell on this because we're running a bit of time, but when you have a point spread function that is a combination of two 1D point spread functions, it makes life even easier in that you can do all of your operations in two 1D operations, right? A set of two 1D operations. And so if I want to convolve f, with h1 first, then it's just a one-dimensional convolution of my image for each value of y. That's just fixed. I just say, okay, at a specific value of y, let's do the convolution in x. You just raster down and do a set of 1D convolutions, for example. And then you have output from that, and you raster down that for each value of x and just do your y convolutions. And so now if this thing was, say, 256 by 256, you'd need 256 1D convolutions in x, 256 1D convolutions in y. That's really fast to do that. And back in the old days when it mattered about computer speed, this was actually an important phenomenon, because a 1D convolution is easy to do. Right? You can do it blisteringly fast. 2D convolutions now on modern computing are pretty easy to do as well. So you can just do the 2D integral actually just as well. So here's an example of stepwise 1D convolutions. Here's our function fxy, and you recognize what this is, the brightness level. So here I have a high value. Let's say this value is 1,000, and let's say this value over here is 500, and the value here is 100 and the value here is 0, right? So it's just a map of brightness as a function of position. But when you look at that map, fxy, you say, well, okay, that's a sagittal head, right? There's a human head. It's like right down the midline, okay? So you can see the tongue and the spinal cord, neck. When we look at this brightness and we say, okay, let's do a 1D convolution of this thing with h1x. So we take basically each y value or each row of this image, and I do a convolution with h1. And that's going to blur us in the x direction. We get this as the output. You can see if I look at edges that are in the x direction, like the edge of the nose here, the edge of the back of the neck, when I move in the x direction, it's blurry. However, if I go north, if I go up in y, it's still pretty sharp when I go across the y direction. That's because we have not done the convolution in y yet, right? And so it's just blurred the thing in one direction. And now I do the convolution in y, and I get a fully two-dimensionally blurred image. Our point spread function was characterized by h1 times h2, right? And this is what our result is. This is our gxy. That's the output. Okay. And we'll see, as we move on in the course, you'll see like what kind of MR image would produce this versus this, right? I can make this MR image, it turns out, in maybe 35 milliseconds. This one takes 3.5 minutes, right? So there's trade-offs between being able to produce an MR image that looks like this and an MR image that looks like this, right? And you can see, we'll see why it's blurred like this when you look at the point spread function of that process of imaging. When we've tuned all our parameters on the MR image, we're making a point spread function, right? And the point spread function we get will look like this when we take 35 milliseconds, and it'll look like this when we take 3.5 minutes. This is, if you know no other transform in the world, in life, this is the one to know. It's called the Fourier Transform. And it takes a look at a function, looks at a function and says, what frequencies are in that function? Let's take a few really trivial examples to start with. If I have a sine wave, right, and I say, what frequency is in that function? Well, there's one frequency, and it's that cycles per second. If I have a function that looks like, say, a triangle, it's an amplitude that goes up and it stops and it goes down and it back to zero like that. And ask, what frequencies are in that function? So there is no single frequency, single sine wave that makes that function. You need to compose a set of sine waves together with different coefficients to make that triangle, right? And so the Fourier transform is the transform you take to figure out what that composition looks like. Okay? And we'll take a look at an example. So algebraically, it looks a little bit obtuse at the beginning, right? When you first look at it, like, oh man, I got an integral here. What am I integrating over? Integrating over x and y, and they appear up here too, right? In the phasor. This, remember what this is? This is e to the minus j theta. This is a theta, all right? And so as I'm doing the integral, the theta is winding around, right? So it looks a little complex, right? But you're basically multiplying your function of which you want to pull out the components, like what frequency components are in there. You're multiplying it by this phasor and finding out what is the value at a specific value of u and nu, right? So I set these two things, set one, set two, say, let's see what it is when I set this to one, this to one. Do the integral. So I multiply my function by this phasor that's rotating at these different speeds as I go through the integral, right? And that gives me the value at 1, 1. Okay. The inverse Fourier transform is defined such that we get f of x back when we take the transform of this thing. Okay, and so to do that, what happens is the negative sign goes away here in the exponent. Okay. And oftentimes there's some normalization factors that will go in front of here, depending on how you want to normalize it. But the inverse transform looks a heck of a lot like the Fourier transform, right? It's basically the same function. It's just the thing spinning the opposite direction. So, okay. So to get an idea of the Fourier transform in time and frequency, so often the first time you get introduced to the Fourier transform, it might be in music or audio, where you have a microphone picking up a signal that's vibrations. And so it's a 1D signal of amplitude vibrations in your microphone. So when you look at the oscilloscope, you see this oscillation, right? And so that function, that oscillation of amplitudes can be described as a set of numbers. G is a function of time. Okay, so we got a bunch of numbers. And then when I take the Fourier transform of G, right, and I multiply it by e to the minus j 2 pi f t, and here remember t, we're integrating over t, and f is the parameter I set. I get whatever the amplitude of the coefficient for a specific frequency, and that frequency is f. So if it's like 440 hertz, I stick that number in there and I calculate this integral from this thing and say, how much of that sound is at 440 hertz? You know, of all of the frequencies that are working together to make that sound. And given the spectrum, I can take the inverse Fourier transform of the spectrum and reconstruct the actual waveform itself, the original sound waveform. So I have an equivalent amount of information in the spectrum as I do in the original time domain signal. And this can be used to your advantage a lot, right? If you want to compress something and you have, say, I don't know, 100 seconds of sound, and you're trying to figure out what are the really important features of this sound wave? If you look in the Fourier domain, it can tell you what parts of the Fourier domain are just isn't any representation in that sound wave, so you can just ignore it. And that gives you hints as to how you can compress the representation of that sound wave into fewer numbers, right? And so that's used to some extent. For example, if I had a sound wave which was a pure tone, let's say again, let's go back to our A440 example, and I have 10 seconds of that sampled at many kilohertz, then I had thousands of numbers giving me the amplitude, right, as a function of time. When I take the Fourier transform of that, how many numbers do I have to store? One. That's it, right? So the whole thing compresses down to one number, right? And so that kind of compression is very helpful. And understanding what's in Fourier space in medical imaging is very important, because when you take MR data, you are sampling the Fourier space of your picture. So you really want to pay attention to the Fourier components that you want to sample, right, to get a high fidelity picture. That's the time domain stuff in sound. What we deal with in imaging is similar to sound, except it's in the spatial domain and then the spatial frequency domain. And so in the spatial domain, you have a function that is a function of position. So let's say that rect function, right? It was zeros and then 1 and then 0. So that's a function in terms of what it looks like. In two-dimensional, rectangle function looks like a big white square on the screen and zeros everywhere else. That's your function. When we take the Fourier transform of that, and we use this as our variable in that Fourier transform, this k sub x, this is a frequency, but it's a spatial frequency. It's how many oscillations per centimeter are we talking about if I had a sine wave in the plane. Okay, and so when we go back to that example of sine waves in the plane, right, these are spatial frequencies, right? This has 4 cycles per field of view, right? If this is 1 centimeter here, this value would be 4 cycles per centimeter, right? This would be 2 cycles per centimeter. That's a spatial frequency. It's cycles per centimeter or per meter. The 1D Fourier transform, when you expand it out, when you want to take the integral itself, you expand this term out such that you have a cos integral and a sine integral, right? And now you can understand that when I have my function here, if my function actually was cos of some specific kx frequency, this integral for every other cos frequency would go to 0. For that specific frequency, you get a spike, right? And so it sifts out, you know, how much of this function has a cosine term at this frequency. Here's the sine term at this frequency. And the minus j is out here. So it's basically asking, this integral is asking how much of the stuff that is added up to make gx looks like cos 2 pi kxx, right? There's a lot of stuff added up to make gx, and some of it's this. How much is sine? Right. This is an example that's all over the place. Every time you do Fourier series and Fourier analysis, you'll see this example. And as if my g of x is this rect, or it's square wave, it's not a rect function, it's a square wave, right? So it's going between 1 and -1, 1 and -1, 1 and -1. That goes on forever. And we ask, well, what would be the components of the sine waves and stuff that I would add up to make that thing? What would be the coefficients, you know, the amplitude coefficients for making that addition, right? Well, you can imagine that the frequency, the basic frequency of this thing is this, right? I go from peak to peak. So that distance, 1 over that distance, is a primary frequency of this function, right? It's like the primary harmonic. And so that's this guy. Okay, so we have 1 sine wave there at omega naught, where omega naught is 1 over this distance, right? And when you add the next harmonic, turns out we skip 1, 2 omega doesn't happen. When I go to 3 omega naught, which is here, and I add it to this one, 1 omega naught, I get this function as the sum of those 2 frequencies. When this plus this, I get this. It's starting to look more like a square wave. It still doesn't look like one, but it has a sharper ramp and it has more of a flat top. And then I jump to 5, and its amplitude is 4 over 5. So it's smaller, right, in relative amplitude than the primary or the secondary. And then I get 2 bumps on the extrema and a sharper edge again, right? And so as I do this and add higher and higher and higher frequencies, we will eventually get as close as we want to get to this square wave. Eventually, you know, we'll just stop adding stuff in because they get too small, and it doesn't really change things compared to our dynamic range of measuring with our practical device, right? Mathematically, this goes on forever, right? There's an infinite series, and then this is infinitely sharp. This is a vertical edge, right? Practically speaking, we're probably going to cut this off at some point and just, you know, use our approximation. Computing some Fourier transforms. So what is the Fourier transform? Like we know a few functions now, right? We know we've looked at the rectangle function, and we've looked at the delta function. Okay, so those are 2 functions we have in our pocket right now. Let's ask ourselves, what's the Fourier transform of a delta function, right? Just think about it for a minute. A delta function looks like this. It's 0 right up until the origin, and then it spikes off to somewhere, who knows where, and it comes back down and it continues at 0, such that when you integrate underneath it, you sift out the value of a function at 0. So it's a really sharp spike, right? And so you say, well, how many darn sine wave frequencies would I need, to build that thing? Because that thing has a very sharp edge and it's very peaky, right? It's got a very small peak. So it turns out a function like that is called to be, it's a very high frequency function. It has these ridiculously sharp edges, right? And so it turns out when you take the Fourier transform of that, and you can do this quite easily, it just sifts out the value of this function, right? Remember what the delta function does when you integrate across a point. So at 0, we just take whatever the heck this function is at 0, and it's 1. So that means for all frequencies, for all values of mu, this function is 1. So as I plot it as a function of spatial frequency, it just stays constant. It just says, oh, I need higher and higher and higher and higher frequencies, all at the same level. Right? And if we set the delta function off from the origin, we get the same thing, except we get it at a specific frequency, right? It's 1 for everything, but it has a phase shift as we move along in frequency space that is equivalent to whatever our offset is. So we have equal magnitude of frequencies out at those values, but to shift it off, we need to add a phase shift to those values as we go up, and that shifts the delta function. So the rectangle function, how does that work out? So the function itself is 1 between -0.5 and 0.5. So all we have to do is, this integral is normally -infinity to infinity. Since the function's 1 between -0.5 to 0.5, then we just change the range of integration, and we're done there, and the function's 1. So it's just the integral between these 2 points of this function. Right? When you do that, and you can do that quite easily because we know what the derivative of e to the x is, and we know what the integral of e to the x is, right? Those are easy to do. You get this as your output for that integral, right? And when you look at this, it basically turns out to be sine pi kx over pi kx, right? So it's a sine wave that's oscillating as a function of our spatial frequency in the frequency domain, and it's decaying as 1 over kx, or 1 over r, right? So it's an oscillation that's decaying, right? And we saw a picture of that before. So here's a diagram. Here's our super sharp function that has a lot of high frequencies. And then in the Fourier transform, it's saying, oh yeah, I've got a lot of high frequencies. In fact, all the way out to infinity, right? I need to add the same amount of power into that signal to build that function. And so this is like, if you're listening to the radio, I don't know what the analogy is now, but if like there's a static charge release or something, you get a pop, right? Like a bang. There's one amplitude that happens really fast and goes away, right? Normally in the real world, things don't usually happen like this. They usually build up a little and then decay away, right? But mathematically, we're just going to call it a delta function if it's small enough, right? And then when the delta function is shifted over, the amplitude of the Fourier transform is still 1. So this is the value of the function as we go through kx here and ky. And on the real axis and the imaginary axis, it's basically a sine wave, but the magnitude of the function is always 1, regardless of what frequency we get to. And the fact that it has this oscillation gives us the amount of offset. So if the offset is higher, this oscillation will be higher. Right? And here's the rectangle function, right? And this looks like straight out of MATLAB, this plot. and our integral, and this is called the sinc function. It's sine x over x, and it looks like this. So as kx gets bigger, right, it oscillates like a sine wave, but it has a central peak and it decays away. Interestingly enough, what's the value of sine at the origin? It's 0, right? Right? And yet the sinc function is not 0 at the origin. Right? So this guy and this guy are going down to the origin at about the same speed right at that point. And so the ratio between them gives you this unity value here, right? Right, right. Exactly. It's like sine as it's going in towards the origin has a slope basically of 1, right? And so 1 over kx, and they just cancel out and you get 1 here. So don't be fooled. Don't look at this and just quickly go, oh, at the origin that'd be 0. Nah, it's not, because you'd have to take the limit as these two things go to the origin. Okay, these. You can compute these transforms and show, the Fourier transform of this guy. We already showed that. That's kx minus k naught. The Fourier transform of a single cosine function, of one cosine function without the j sine part there, right? This has the j sine part in it, right? So you get a delta function. Here, when you take away the sine part, you only have the cosine function on its own. When you take the Fourier transform, it turns out you get 2 peaks, 2 delta functions. And they are at whatever the frequency is of the cosine plus and minus from the origin, right? You get the 2 delta functions. Similarly with the sine function, you get 2 delta functions. But one of them is inverted with respect to the other, right? So it looks like that. Right? It's a linear transform. So if I take a sum of 2 functions, I can equally well take the sum of their Fourier transforms and multiply them by coefficients. And that works in 2D as well as 1D. Duality, okay. So basically what we're going to say is that if you take the Fourier transform of the Fourier transform of G, okay, not the inverse Fourier transform, but the Fourier transform of the Fourier transform of G, you will get G back, but it will be reflected around the kx axis, okay? So in order to get G back, you need to take the inverse Fourier transform, right? That. Okay, so the application of this is that if you have some complex function, right? Say you want to take the Fourier transform of the sinc function, which is kind of a hard thing to do, right? Because the function itself is a little bit nasty, right? It's got a 1 over x, it's got a sign in here, and so you're going to do this multiplication and do this integral. So it can, get pretty complicated algebraically. But we do know that the sinc function was just a Fourier transform of a rectangle. So we're pretty darn close to the answer just by saying, look, if I took the inverse Fourier transform of this thing, I know what it is. It's a rect this way. When I take the Fourier transform of this, because I know it's the Fourier transform of something, I know the answer immediately. And so I can go back and forth between the 2 spaces. I can tell you what the Fourier transform is of many functions right? Because I know they are the result of a Fourier transform or something else. So, you know, if you're taking the Fourier transform of sinc x, then you can just say it's the rect function, but at negative kx. Turns out that the rect function is symmetric anyway, so it's just the symmetric rectangle function. All right, so these are transform pairs. You should know a lot of these that are on this page. In fact, probably all of them, okay? So you should know that the Fourier transform of a constant signal is a delta function. Similarly, the Fourier transform of the delta function is 1, right? The Fourier transform of a delta function shifted from the origin is a function that has unit amplitude. However, it oscillates as we change spatial frequency, right? And that's proportional to how much it's offset. What other ones? Rectangle is sinc. We know that. Fourier transform of sinc is rectangle. It turns out that the Fourier transform of a comb function, which was our sampling function that we looked at before, is a comb function. I think we're going to look at that. And then this is an important one as well. And that is the Fourier transform of a blob, which is encoded or represented by a Gaussian blob, which means as I move off in radius, I decrease as 1 over e as a function of, you know, going off in radius. That blob, when you take the Fourier transform of that, you get a blob in Fourier space centered on the origin. And we'll see that if we add, instead of x and y, we have, say, ax and by, we'll see that the width over here is proportional to 1 over a and 1 over b. But a blob at the origin with a decay out of 1 unit transforms to a blob in Fourier space. Okay, there are a ton of theorems that are used to solve problems when you know the Fourier transform and you're trying to figure out what's going on. And you need to know something about the linearity, or you have 2 images and you're adding them together. All of these properties of the Fourier transform come and go in it as importance. But let's just look at a couple of them. I think, okay. Yeah, let's do this one first. This is one of the most important, specifically for us, when we're doing imaging. And that is that if I have a function, fxy in the plane, we can do this in 1D or 2D, doesn't matter. And I convolve it with another function. Let's say the point spread function, right? When I look at that in Fourier space, what that equals is the Fourier transform of fxy, and that's given as this function here, capital F mu nu, right? So that's its Fourier transform. It's like the continuous God-given transform multiplied by the Fourier transform of gxy. So there's a convolution over here, a multiplication over here. What could be simpler, right? In that I have a point spread function that I need to convolve over my space in order to make the picture look like that which will be achieved by my imaging system once I know the point spread function. But when I look at it in Fourier space, all that convolution, what it results, or what it is a multiplication of a function in Fourier space. So for example, if it's a low pass filter, so that means low frequencies get through, high frequencies get attenuated, then my function in Fourier space will be high at the origin and at the low frequencies, and it will roll off at high frequencies. And it will eventually cut off the high frequencies. It's called a low pass filter. When you're listening to audio and there's a lot of high frequency crackle and noise and stuff like that, you can get rid of it by putting that signal through a low pass filter. Right? We're somewhat familiar with that. if there's a lot of noise in a field of view in an image, then we can say, oh, let's convolve it with a Gaussian that has a width of, say, 2.5 pixels. We'll just convolve the whole picture. That'll smooth out the noise. The high frequency noise gets smoothed out. When I look at what happened in Fourier space, is I took the Fourier transform of my image and multiplied such that the high frequencies got attenuated. And if there's a lot of noise out there, the noise gets attenuated. So this is the theorem I think is responsible for the definition of convolution. Because when you define convolution as reversing G and then doing the integral, this comes out just like this multiplication. It's very easy, right? So it's that's why convolution, I think, is defined as it is. A similar thing applies when you have a picture, which is fxy, and you multiply it by some other thing. So let's multiply it by, what should we multiply by? Say I have a picture, and I've got a whole field of view, and I just want to look at one thing, one area. So why don't we multiply the whole image by a circle with diameter whatever and amplitude 1, and then boom, I basically just get rid of the rest of the picture, right? I crop it, right? So what does that do in Fourier space? It turns out I take the Fourier transform of that whole picture and I convolve it with the Fourier transform of my cropping function, right? And so that's what's going on in frequency space to make that happen, right? This turns out that it seems subtle, and it's hard to kind of come to grips with it, because you're like, well, it's so easy to understand what happened in space. We just cropped it. So what is there more to understand? But cropping in medical imaging means I only have to measure this field of view, right? So if I can ignore this stuff out here, then I can probably make my image a lot faster, because I just need information from this field of view. However, I'm getting signal from all over here. So how do I do that cropping in raw data space? Well, it turns out this convolution is essential to that, right? Because now we know that cropping corresponds to taking my raw data and just smoothing it, right? And asking the question, when I smooth that data, right, how can I get away with putting as few points in there and doing that smoothing and having it show up as the high fidelity image, right? So understanding that this smoothing is occurring in the raw data space is an important feature for figuring out how do we take raw data faster. And then there's some bookkeeping stuff, scaling. If you have a function and you change the axes, then the Fourier transform gets scaled, right? And so you could try this with the Gaussian. It'll be illustrative, as to what happens to a Gaussian if I put an A and a B in there, and then just plug in the formula here, and you'll see what happens to the Gaussian in the Fourier space. What's going to happen is, as I make my Gaussian in real space really wide, so it's slowly decaying, in Fourier space, it'll get very narrow, right? Circular symmetry, reversing. Okay, translation is an interesting one, and that is if I take my object and I just move it, n pixels in a certain direction, what does that do to the Fourier transform? Well, the magnitude of the Fourier transform remains identical, okay, as we can see from this. So the magnitude goes unchanged. It's still there. But what happens is I multiply by a phase, a plane wave that corresponds to the translation itself. So remember the plane waves that we looked at that had frequencies of, in that case, it was mu and mu, but here it's x naught and y naught. So I shift the object in space, and in the Fourier domain, I just multiply the entire Fourier transform with a phase shift that's this plane wave. The magnitude stays the same. Okay? I think that's probably it for the super important stuff. Parseval's theorem is that the amount of stuff in the spatial domain, and how do you quantify the amount of stuff in your image? You could just take each pixel value, square it, right? So it's not negative and positive, just the amount of stuff, the magnitude of it. Or if it's a complex number, just take the magnitude and just integrate all that stuff. So I get a number. That's how much stuff I have in my XY plane. And you ask, well, how much stuff am I going to have in my Fourier domain for that much stuff? And it turns out that those two things are equal. When you integrate the amount of stuff in the Fourier space, it's the same amount of stuff as in the space, which makes sense, right? You can't have a whole bunch of image over here and then just nothing in the Fourier space. It's not going to work. Right? Okay. So what I just described about the convolution theorem is shown in one dimension here. And I believe this is in the book, although I don't have a formula here, so I'm not absolutely confident it's in the book. But basically what we're saying is I have g of x, right? And h of x, I'm going to convolve those in space in x. So we know how we do the convolution theorem, right? So that basically gets written out as the Fourier transform of the convolution. This is the convolution inside this box, right? Inside the square brackets is the convolution of g with h. And u is the integration variable, so it's going to get integrated away inside this brackets, right? But the result of that thing that's inside there is the convolution of gx with hx. So I take the Fourier transform of that by multiplying by this and integrating over x, right? And now we can break this up and move g of u outside here. Do this first, right? And find out that we now have basically the Fourier transform of h here, right? And I still have this integral over u, and so I have the Fourier transform of g here, and it's just their product. Okay? So algebraically, as long as you believe you can move this g of u out here, you can do it. But the order of those integrations should not matter. And so that brings us to this result, which is a huge deal, right? Because when you're thinking about what's going on in real space and in Fourier space, using this convolution theorem is done all the time. Okay, good. So let's go back, I guess, one lecture or two lectures, and we looked at the point spread function directly as that little dot that we imaged. And we now know the point spread function can be characterized by taking a delta function and basically convolving it with the point spread function of the system. We'll get what a dot produces. And when we take the Fourier transform of the point spread function, we get a function called the modulation transfer function, which is now in spatial frequency, right? And so this is the function that if we had the absolute true Fourier transform of the object we're imaging, right? So we've got the God-given Fourier transform here of the object we're imaging. In imaging space, I convolve it with my point spread function to get what my linear shift invariant imaging system is going to give me. That is equivalent to multiplying by the Fourier transform of the point spread function in Fourier space. That will produce the Fourier data of my final image, right? And this is called the modulation transfer function, and it is, to repeat, the Fourier transform of the point spread function, right? So if my point spread function is a Gaussian, the Fourier transform of Gaussian is a Gaussian in Fourier space, and that's what I multiply the Fourier transform of my image to get the frequency components that I'm going to see in images I make with a system. So if this is the relative amplitude of the frequencies that are passed through the system, right? Let's think about it a second. This system out here, system C, still has some amplitude for these high frequencies, right? And therefore, the point spread function in image space will be much smaller in diameter, right? It will be the thing that I'm smoothing my image with will be a tighter, thinner function. Right? This function, because I'm attenuating many high frequencies, they're gone here, will be a function that's broader. And when I do that convolution, it will blur the picture more. So more high spatial frequencies are missing, right? We can look at that absolutely directly with this example. Here is my function that we started with that was the sagittal image of somebody's head. This is the magnitude of the Fourier transform of this picture. Okay, so each one of these bright dots here is the relative magnitude of the Fourier coefficient at a specific spatial frequency, right? And this is usually we take the logarithm of this function to compress the values that are around the origin because they're so much higher than all of the other values. So we compress it to look at it. And if what we do is we just take this data and we take the inverse Fourier transform of this, we get our picture. And it turns out in magnetic resonance imaging, we collect this data. That's what's in our machine after we've finished doing our data collection. Then we do an inverse Fourier transform and boom, we get the picture on the screen. If we multiply this Fourier data by a function that depresses the high frequencies by out in this corner here is a high frequency. These are plane waves of very, very high frequency. And we damp those down, we get this picture. So now the details and the high frequency edges are gone, right? And if we do it more, we tighten that down and filter it more. It's a low pass filter. We basically get a super blurry picture. Now, the mean value of the brain here is the same as the mean value of the brain in a large section over here, but you can't see any of the details, any of the edges and points and things like that get smoothed out. And so that is the convolution theorem, visually represented. And it's really appropriate for NMR because this is your raw data for NMR. Yeah.
I suppose it kind of makes intuitive sense because the high frequencies would be like shorter wavelengths.
Correct.
And that would be smaller things.
Correct.
So if you get rid of those, and you have the low frequency, those big waves,
Just get blobs.
get blobs.
Right. And so when we're creating that square wave, basically we have attenuated all those higher frequencies that put the edge on that square wave. And so all that's left is a smoothed square wave. And you can see as I go to the edge here, it's a very smooth ramp up as opposed to a sharp edge. Right. So making those edges, making points, you lose that ability when you get rid of all these high frequency short wavelength components out there. Okay, great. And we'll take it up from there on Wednesday.